So today, I'm not here as a scientist, I'm here as a Girl Scout. And what I'm going to do is some fast talking so that we can get to the part where you can do some talking and ask some questions. The first thing I want to tell you is that anyone can be a scientist or an explorer, and in fact, it doesn't matter what you study, because at any point in your life you can change and do something else until you're dead. And I wanted to tell you that I majored in music. And that wasn't enough, so when I went back to graduate school, I majored in music again. So on the third try, I figured out, oh, maybe I'll do science now. And so even if you think you don't like science, or you think you're not good at science, or you think you're not good at math, those are not good excuses. Always do things that you want to do, whether or not you think you're good at them, because you may not find out until you start to do it. So, we didn't have daisies back in the Stone Age when I was a Girl Scout, so I started with brownies, and then I got to juniors and I got to cadets. I was never a senior. But my last troop was 2017 from Bethesda, Maryland, of the nation's capital council, and I just wanted to tell you I still remember that. So I've gone to all kinds of cool places, as you already heard. This is a Girl Scout flag given to me by the Girl Scouts of the San Fernando Valley in Southern California, which I brought with me to Antarctica in 2005. And that is just to tell you that whether or not you think you can go to these exotic places, you can go. You just have to decide you want to and then figure out how to do it. And I'm going to tell you a little bit about how you figure out to make these things happen for yourself. This is in Canada. It's called Llewellyn Glacier. It looks like it's a painting, right? But that's just how it looked that day. The ice is blue because water is actually a blue molecule. Oceans don't look blue because they're reflecting the sky. They really are blue. It just takes a bunch of water for you to see the color. And the reason why they're blue is because the physical property of water that is so amazing, beyond the fact that it lets lots of stuff dissolve in it, is that it holds heat really well. And the reason it holds heat really well is because it absorbs light at a certain color. The color being one you can't see. It's called the infrared. And the infrared is a wavelength of light that is essentially heat. So the thing about water that is the coolest thing about water is that it holds heat. It absorbs in the infrared, and that means when it takes in sunlight, it's spitting back out or reflecting all the other light. So you get all the blue stuff reflected back, and you're sucking in the red and the infrared. So next time somebody asks you why water is blue, now you know. Now I wanted to address some tough questions here. These are not the questions you address when you're trying to develop technology. The reason why we develop technology is because we need stuff to help us extend the range of our senses. We can all see at least a little bit, and even if our eyes don't work, we can see with chemicals and we can see with touch. So when we invent things like a pencil, a computer, a spacecraft, Angry Birds, any of that stuff, it's to help us extend the range of our senses. So the reason why we explore is because all biological things do this. My dog does it, bacteria do it, we do it. It's our destiny. The value of exploration is important because not everyone pays for all the exploration they do. Sometimes it's a very expensive endeavor. For example, I'm part of a team of scientists that have just landed a robot on Mars, and we are all working day and night to get the most we can out of this mission. In fact, I just came from Southern California last night where we're working on it. So in that case, where we're going to another planet, we need a lot of technology and we need a lot of people to make it happen. It costs a lot of money. So how do you get value for the money you put into exploration? We're going to talk about that. Then we'll talk about how you personally can make exploration happen. So, here's some things that we have to know the difference between them. Adventure is a thing that humans do because it's fun. So if we want to go on a roller coaster, or we want to try and sneak out of the house at night and stuff like that, we do it because we think it's a thrill. And sometimes we do adventures whether or not they're good for us. It's a thing that we do. It's an instinct that many humans have. And the reason for that instinct is to help us move out and explore. Lots of times you'll see somebody doing something and you'll go, what are they thinking? Well, people do behaviors not always because they're thinking. They have behaviors that are sometimes hardwired in to help them survive in a more global sense. Sometimes they have behaviors that are not good because something went wrong. Something influenced people to adapt a behavior that they might need that used to be for something else that now is being used inappropriately. Adventure is something that can be used appropriately or inappropriately. If we go bungee jumping, our mothers will all say, that's inappropriate. If we decide we're going to go on an expedition to the rainforest of Brazil to try to discover new pharmaceuticals to cure cancer, probably people will think that's a pretty good adventure. So lots of things are on a spectrum. Bad, good. And so we make choices to use things for either not such great reasons or really great reasons. Adventure sometimes helps us explore. Exploration is how we recognize opportunities and threats in our environment. Opportunities could be things like, where is the food? When you're a human, it could be more like, where is there a job? Or what school can I go to? Or something like that. Or where can I live? That's an opportunity. A threat is, how about a predator? Is there something that's going to eat me? If you're in Southern California, you don't let your cat out at night because a coyote will eat it. That's a threat. So when we explore, we're trying to learn what the opportunities are and what the threats are. Science is a process by which we know things. There are lots of ways that we can know things as humans. And they're not incompatible, they're just different ways. So science is a way where we use a very specific technique to learn things. And one way that we can make exploration valuable is by using the scientific method when we explore so that we can add value to our exploration. And that's how, when a country or a company or somebody pays for an exploration, it's a way we can bring value as an explorer back to the person who paid for it. Science. Now, there's lots of stuff to explore at all sizes, all distances, and I'm not going to go through this chart, but it's just to tell you there's very teeny tiny things you can explore and very humongous things you can explore. And the same goes for time. You can explore processes that happen right now, or you can explore things that happened eons ago when we're trying to understand, for example, the evolution of the Earth. All of these are open to you. Operators are standing by now if you declare your intention. Have at it. This is called the Taylor Basin Dry Valley in Antarctica. And I want to show you something really cool. See how there's like dark stuff in the middle of the screen? And then like this stuff is lighter here. You can see the difference between these rocks and those rocks? So I took some people down there to try to figure out how microbes living in rock do it. Because, you know, they're in rock, right? So how do you live inside a rock? Well, it turns out that the microbes that live in the rock are able to live in this light-colored rock because iron that weathers from the dark-colored rock turns into dust as the winds blow on it. That dust blows over and gets on the top of this light-colored rock. And then the microorganisms that live in that rock take that iron and they actually breathe it. And they take an electron away from it, and then it turns into rust. And so the reason I'm showing you this is to tell you that when you go into the environment, you might just go in there and go, wow, it's really cold. But another thing you might do is say, wow, those rocks are dark and those rocks are light. I wonder how this all fits together. Well, then you look more closely at the lighter rock and you say, hey, there's rust on this rock. And then you kind of scrape it off a little and you go, hey, there's somebody living in this rock. And you see there's a whole story here of how everything fits together. So it is an adventure, and it's pretty cold when you're there, and I camped there for 5 weeks. So to make myself feel better at night, I would read stories about mountaineering disasters so I could think, I really have it good. But the important part of the story is, when you go and you explore this environment, you have an adventure, which is what makes you want to go down there because it's so cool. But then you start looking really carefully at all the things in the environment, and that's how you learn the story of how the living things do it. This is on the other end of the planet. This is the Arctic. And there I am in the blue sweater with my friends Jan and Jake, and I'm having a cup of tea because you see that tiny little boat way in the distance down in the fjord? Well, after we took a little inflatable boat to shore, we hiked up to the top of this volcano. So we desperately needed a cup of tea. And a bathroom, but alas, there were none. This is what that ship looked like up close. And see all that red stuff in the background there? That's how high we hiked. So, what I do for a living is try to figure out how things live in different places on a planet so that I can then apply that information to trying to figure out what planets other things might live on and what the requirements would be. It's kind of like real estate appraisal, but on another planet. And in fact, that's what I'm doing right now on Mars. Well, not right now, I'm talking to you, but as soon as I fly back to California, I'll get back to that. So this thing, habitability, I can't even say it easily, especially when I got up at 3:30 in the morning. But the point is, if we can understand what things about our environment make our environment livable on Earth, then we can know if we're doing something to foul up the environment and make it so we can't live in it. And we can also recognize those features about an environment on another planet that might make it habitable, so we can begin to predict which planets not in our solar system might be more Earth-like than others. Why do we do this? We do this because exploration is a biological imperative. An imperative is something that we just do because our wiring, our DNA tells it to do it. So we explore and we ask these questions because they do have value and relevance to life on Earth, but I can't help it. It's a biological imperative. So the next time you're studying something really hard and you are just, really trying to figure something out and your mother says, please set the table, you can say, I can't, I'm studying because it's a biological imperative. So if you saw one of these things, you'd have some sense of what it is, right? Because you've seen one of them before. And you might even have the expectation of its behaviors. Or it could be producing products, which you have to do something with. So your pattern recognition from your experience as a human being tells you that you might have a sense that this was a living thing. Now, if you've read a lot of comic books, and I have, you might think that this is a living thing that's on another planet, right? Because that's how we depict aliens. If you look more closely at this, you begin to see some things about it that kind of remind you of that other thing we just looked at. It's got two of those little black things, see? It's got that squiggly thing there, and it's got these things, and it's got two of these things, and you begin to say, this thing has some symmetry to it, right? The left side is kind of like the right side. And then you begin to notice other things. Oh, look at that, it's all green. I wonder if it's full of chlorophyll and is a photosynthetic life form. So you begin to look at things that are not exactly like something you've seen, but close enough so that you can make inferences about it. Well, the truth is, on other planets, we're less likely to see something like this thing or the thing that came before it, and more likely to see something like this. Because on Earth, the bulk of all the diverse organisms we have is microbial. These things are most of the life on Earth, and they're the most robust and resilient. They can live in really hot places, really cold places, lots of pressure, not so much pressure, lots of radiation, even very dry, extreme chemicals. So when we try to figure out how you might have life on another planet, we typically try to think of life in terms of the requirements of microbial life. So I boil it down into two really simple things when I'm trying to figure out if an environment is livable. I think about what kind of life might be there, trying to cleanse my brain of notions about life from what I know of it on Earth, and I just think of life as it's made of something, and it does something. So, if it's made of something, it's got stuff, and it's arranged in 3 dimensions, or 2 dimensions if it's, really flat, and it does stuff. And that's how you do it. You figure out what the life is and what it does, and then you figure out what requirements that places on an environment. See, it's easy. When you go to an environment like this, it gets less easy because it doesn't look like there's any requirements being met. It looks too cold. It looks like there's no life. But in fact, if you start looking in the rocks, you see pretty quickly that they're teeming with microbial life. So by the way, this is my camping spot in a place called Battleship Promontory in the McMurdo Dry Valleys of Antarctica. And some key important things here. So this yellow tent is the science tent where the instruments were. Everybody see that orange tent with the guy standing right next to it? That was the bathroom tent. Sadly, it's relatively close to the kitchen tent, but at least separated by enough distances to be respectful. And then the rest of them are sleeping tents. So the key thing here is we went here to try and figure out how microbes that live in rocks can actually do it when it's this cold and there's no other animals and there's no raw materials except the iron that's in the dark rocks in the bottom of the basin. Because we want to figure out how stressed life can be here so we can imagine, well, is it possible to have it on Mars? So, back to Mars. Most of you who have seen the television or gone on the internet or seen a newspaper know that we landed on Mars in August, and we've been there now for a number of weeks. This is a picture that the camera on the end of our robotic arm turned around and took looking up under the belly of the rover. So that's actually on Mars. And our goal is to try to figure out whether or not Mars has ever had a habitable environment on it. And Mars is about a little more than half the size of the Earth, and they have very different conditions. The Earth is pretty warm by planetary standards. It's wet. It's got a nice, thick, juicy atmosphere, which is good. Otherwise, we would have nothing to breathe. And it's got a big magnet in the center of the Earth. And that magnet is important because it keeps cosmic rays from coming down here and frying us and mutating us and protects us so that we can have life. Mars, no magnetic field anymore. About 4 billion years ago, a giant storm of rogue asteroids came through the inner solar system, smashing into all of the terrestrial planets, that is the rocky planets, Mercury, Venus, Earth, and Mars, and bombarding them, making huge craters. Earth was pretty stable because it had this best friend forever we call the moon, and so the Earth was able to survive this, and Mars, even if it had developed life at that point, may have lost it. So what we're trying to do is see whether the rock record tells us any clues about whether or not this has ever happened. And so as we move with our Curiosity Rover, what we're trying to figure out is whether anything can live there. And we're in a place called Gale Crater, which is very close to the equator of Mars. So it's the most hospitable place we can find on Mars right now. So if ever there were life on Mars, it's probably one place where the evidence is preserved, which is why we chose that landing site. I'm going to skip through the requirements of habitable environments because I really want to get to a point where we have some time for you to ask some questions. I just want to remind you that life has physical requirements as well as chemical requirements. You kind of already know that. It can't be too hot, can't be too cold. If you had too much gravity, you wouldn't be able to get out of bed. If you had too little gravity, you might fly off the Earth. What would make this planet have too little gravity? If it was too tiny. If it's too tiny, it's hard to land a rover there, right? And that's one of the challenges of going to an asteroid. You've got to pick one big enough that there's enough gravity that you don't slide off. This is the picture we took the first night we landed on Mars of our own shadow. And see this mountain in the background? That's Mount Sharp. We're going to climb up that mountain, but not for a little while. We're still doing some checking out of our rover. And what I wanted to show you here is these are pictures of actual parts of us. And my favorite one is the picture of us, the Curiosity Rover, which you can see in the second box from the right. It looks like a little gray dot. That's actually a picture taken by a satellite orbiting Mars of a rover sitting on the surface of Mars. How cool is that? So I already told you we're kind of close to the equator. It's a great big crater. It's about 93, 94 miles in diameter. And that mountain that's in the middle is very tall. It's a lot taller than anything on the East Coast. It's even taller than Mount McKinley. And it's got a lot of layers on it that if they were cut through, it would look kind of like the Grand Canyon. And in fact, I got a picture of the Grand Canyon here on the right and a picture of Mount Sharp on the left. And it shows you relative heights of things, and you can see these many layers in the Grand Canyon as well. So that's another clue about how to explore. Go to the Grand Canyon, or go to the Sidling Hill Road Cut in western Maryland, and look at the layers in the rock there. The layers in rock tell the story of the previous processes, and that's how we learn about our history, by looking in the rock. So Curiosity Rover right now is very close to the central mound. You see that black diagonal stripe in the picture on the right? That stripe is actually dark, dark black lava sands. Those are dunes. It's kind of like the black sands in Hawaii. And we're very close to them, and we hope we'll be scooping some sand soon. One day, before we took the lens cover off of the camera on the end of our robotic arm, we turned it around and we took a picture of our mast. Now the lens cover is off, and we're getting amazing images, and they're all available on the NASA website. All you have to do is Google Mars Science Laboratory or Curiosity Rover, and every day when pictures come down, you can get fresh ones. So every day, we do our business in a very structured way. We have different kinds of days on Mars. We don't call them days, we call them sols, because a day on Earth means one rotation of the Earth. Well, we rotate at a different rate than Mars rotates. Mars is a longer day, and when Mars is facing the sun and its light, it's not in sync with when we're facing the sun and its light. So we call those sols on Mars and days here. And when we print out our work schedule, trying to send instructions to the rover and getting back information, it's really complicated because we're on an Earth day and our family wants to know where we are. So part of us are on Earth day, and part of our brain, we're kind of on Mars day, and the other part of it is we're simultaneously in California operating the rover, so we're thinking about local mean solar time on Mars, Pacific daylight savings time in California, and Eastern daylight time, because that's where my main laboratory is, so it's very confusing. And since I got up at 3:30 to drive here, I'm really confused. So on any given sol, we do different things. Some days we're driving the rover, as we did a little bit yesterday. Then when the rover stops at night, we do experiments with my instrument, and we did an experiment last night to inhale some atmosphere and try to see whether we can find organic molecules in it, and the data's coming down in about 3 hours, which is very exciting to me. Some days we just take pictures with our remote sensing cameras and try to get the lay of the land by looking at images. And other days we actually take things that are on the end of our robotic arm and we place them down on rocks. And that's how we make our quantitative measurements, or things like, oh, this thing's made of copper, molybdenum, silicon, and so forth. So I want to tell you that we have to evolve ourselves technically in order to evolve our information scientifically. And the way we do it is everything that we've already learned, we feed into the next thing we try to do. So we always try to push the boundaries and do something bigger next time. So if you look at the little bitty Sojourner rover, that thing was tiny. It was about as big as 2 shoeboxes. That was in 1996. If you look at Spirit and Opportunity, which are still on Mars, and in fact Opportunity is still bringing home science, even though it was only designed to last for 90 days, many years later, that was a lot bigger. If you look at Curiosity, that thing is a monster. It's as big as a Jeep, and it weighs a ton. I mean, literally a ton. And it's got all these zillions of scientific instruments on it. But the only really important one is, of course, my instrument. Its name is SAM, for Sample Analysis at Mars. We determined it was actually a girl. And SAM measures gases. What it does is it either sucks in the air directly, or it takes something that the rover arm scoops and dumps into a little funnel on top of the rover deck, and then we seal that cup of the stuff that the rover dumped in up against the oven, and we heat it to 1,000 degrees Celsius, which is a lot of heat, until it becomes a gas. So basically, if it's not a gas, we can't measure it. We take this gas, we send it into an analytical tool called a mass spectrometer, and that tells us what chemical elements and what molecules are in the material. And so we haven't scooped anything yet on Mars. We're preparing to do that in the next several days. And we just did our 4th atmospheric experiment last night. Results to be announced this week. So I'm going to skip this stuff. I want to show you these URLs. You're probably not going to remember them right now, but I think probably we can arrange to have you get them. Just Google Mars Science Laboratory or Sample Analysis at Mars, and you'll get these, and you can find out more information. Now, I just wanted to say one more thing, and then we'll take a couple questions if there's time. I'm hoping there's time. All right, good. So, when I finally decided to study science in graduate school, I took a course called Petrography. And in petrography, what you're trying to do is learn about how to recognize all the minerals that are in rocks. And the way we do it is we take a rock and we slice it with a saw into a really thin piece. We call it a thin section. And I mean really thin, like vanishingly thin, so that it's kind of transparent. So only really dark minerals show through it. And then we look at that under a microscope, and you see stuff that looks a lot like this. So these are called petrographic thin sections, and those are all crystals. So I took this class, and it was fun, and then I graduated, and I got a job at the Jet Propulsion Lab, and I'm in there in my office, and some guy comes to see me, and he is just kind of staring around at my bookshelf, and he goes, "Oh, I see you have this book." He said, "Did you ever see the self-portraits this guy put in his book?" And I said, "No, what are you talking about?" And he says, "Well, in every petrographic thin section, he did a little self-portrait." And I said, "Really?" So I whipped out the book, and I looked really carefully, and sure enough, on every single page where he draws thin sections, in at least one of them, there's a little bald guy smoking a pipe. And I thought, holy cow, I would never have known that was there if this guy didn't come to my office and tell me this. So the reason I'm telling you this is because it has everything to do with exploration. You have to keep a very open mind. You have to look at everything